Hello everyone, welcome to my channel Chemistry by ANR. In this session, we are going to deal about disaccharides, especially sucrose, lactose and maltose. Their linkages, their monosaccharide units from where they are obtained, or the monosaccharide units that will be obtained on hydrolysis, and whether they are reducing and non-reducing sugars. So this is what I was talking about, disaccharides. Disaccharides are the carbohydrates that on hydrolysis produce two monosaccharide units. So obviously in disaccharides, if the structure is seen, the two monosaccharide units are joined by a glycosidic linkage, which is often termed as oxide linkage, but I will prefer to use the term glycosidic linkage, and I'll tell you how the linkage is obtained. So, disaccharides on hydrolysis with dilute acids or enzyme, they yield two molecules of either the same or different monosaccharide unit, like sucrose. Sucrose is a disaccharide. When it hydrolyzes, it produces equimolar mixture of glucose and fructose, both belonging to the D series, and sucrose is known as invert sugar as the optical rotation, the specific rotation of aqueous solution of sucrose gets inverted on account of greater extent of levo-rotation of fructose than the dextro-rotation of glucose that converts sucrose from a dextro to a levo in its aqueous solution. Now we can see that sucrose, what is the nature? It is a non-reducing sugar. What is the meaning of this term non-reducing? It means sucrose is unable to reduce toluene and Fehling solution. What is the reason behind it? We know the anomeric carbon of glucose is C1 and the anomeric carbon of fructose is C2. So in the structure of in the structure of sucrose, we can see that the anomeric carbon of glucose and the anomeric carbon of fructose, they are chemically bonded as a glycosidic linkage by the elimination of H2O. So here, if you see the structure, you may think it's a beta D fructose, and so the anomeric carbon should have OH at the top, that means above the plane. But the structure shows OH below the plane. If you see the structure of beta D fructose that you had seen previously, the Hawat structure, the oxygen is between C2 and C5. So this is the fructose structure, and if I say one is C2, the other is C5, and in C5 you always have to form this first CH2OH, which is carbon number 6, and this is H. So each position is having bonds like this, and in C2, if I say it is beta form of fructose, then obviously OH is on the left hand side in the Fischer projection and above the plane in Hawat structure. So here it is CH2OH as carbon number 1. Rest of it in carbon number 3, it is what? HOH. And so this is OH and this is H. So each structure, each carbon has undergone an inversion. That means upside down. The groups that are above the plane are below, and the groups that are below the plane are above, on account of which the configuration at C2 gets inverted and OH is below the plane. So now, over here, that doesn't mean that it is alpha form. Why it doesn't mean it is alpha form? Because equally the configuration at C3, 4, 5 has undergone an upside down. So now, by the elimination of H2O, the glycosidic linkage is formed and the anomeric carbons are chemically bonded, on account of which sucrose is a non-reducing sugar. The two monosaccharide units are held together by a glycosidic linkage between C1 of alpha-D-glucose and C2 of beta-D-fructose, which are the anomeric carbons. They are the anomeric carbons of glucose and fructose respectively. Next, I have already told you why it is invert sugar. Because the hydrolysis of sucrose brings about a change in the sign of rotation, means optical rotation. Do mention optical rotation. Moving on to maltose. Maltose is a disaccharide. On hydrolysis, what does it give? It gives 2 units of alpha-D-glucose. So the monomeric unit is same, but 2 such units are obtained. So it is a disaccharide, and alpha-D-glucose has anomeric carbon as C1. So one unit has its C1 bonded, but the other unit has its C1 non-bonded or free. Since the anomeric carbon is free, for that reason, it is capable of reducing toluene and phelline, for which maltose is a reducing sugar. Because of the free aldehyde group that is present in C1, the anomeric carbon is free. So do mention that the anomeric carbon of alpha-D-glucose in one of the unit is non-bonded or free, and so it can reduce toluene or phelline solution. Moving on to lactose, which is a disaccharide. Now, lactose is known as milk sugar because it is found in milk. And it is composed of beta-D-galactose and beta-D-glucose linked in a trans manner. We can see that the glycosidic linkage is in a trans manner. And so what is happening over here, when we see the structure of beta-D-galactose, what do we see? That the OH, okay, over here it is a beta, so OH over here was above the plane. And when you see the structure of beta-D-galactose and beta-D-glucose, please compare all the positions, be it C1, C2, C3, and note that at C4, what is happening? The structure is getting altered because the C4 of beta-D-glucose has OH below the plane and H above the plane, which is getting altered in the structure of beta-D-galactose, for which we can see that beta-D-galactose is epimeric at C4. Okay, that means galactose, beta-D-galactose and beta-D-glucose are epimers. We have seen what are anomers. Now what are epimers? Other than the anomeric carbon, if there is I will say any other position where the configuration is getting altered, that means the configuration is getting altered in such a position which is not the anomeric carbon, not the anomeric position, in that case they are epimers. So beta-D-galactose is epimer of beta-D-glucose and it is epimeric at C4, and this glycosidic linkage is a trans manner. Please note that in beta-D-glucose, the anomeric carbon C1 over here is free and non-bonded. It's free and non-bonded, for which it acts as a reducing sugar. So that's all for disaccharides. In the next module, we are going to discuss about polysaccharides. Till then, bye all of you.